Okay, we had said that 600 million tons of hydrogen fuses into 596 million tons of helium. Now, this is kind of an oddity because we know that the hydrogen is made up of just protons. Helium is made up of protons plus neutrons. Neutrons weigh more than protons, and so this is an odd sort of thing because you have these two protons plus two things that weigh more than protons, and the four of them together weigh less than four protons. And so what's happening is when you put it all together, there's a reduction in overall mass. Rather, if you pull them apart, you have an increase in mass, and that we know that mass and energy are interchangeable. So this has to do with what we call the binding energy of the nucleus beyond the Loveless course. But it's the nuclear physics of how all that works, how release all that sort of thing that makes how nuclear reactors work. The sun does this in a multi-step process. It obviously can't be just protons come together and turn into helium. So the first step of the process, what we call the proton-proton chain, is that two hydrogens come together. Now, they don't want to come together. They don't want to come together because they repel each other. And so it takes an enormous amount of heat and pressure. The pressure pushes them close. That still doesn't force them together. The heat makes them move around so much they bump into each other. And what happens is, for a fraction of a second, we have these two hydrogens in there. But it takes so much energy to push things together. Now, in physics, we learned that work is force times distance, okay, and that work is change in energy, okay. And so it takes an enormous amount of work because you have a huge force to shove them together, so that work increases the energy. Eventually, you have so much energy that you start breaking down the quarks in there. You have too much energy to have just up quarks and down quarks. You have down quarks and up quarks, and this turns one of the protons into a neutron. And now they're able to stick together without a lot of force. In fact, there's another force called the strong force, which holds them together, strong nuclear force. And now what happens is with now you don't have to have all this extra energy pushing it all together. That extra energy is now gone, and that is released in the form of that less. You end up with this weighing less mass. This energy goes away. Okay. Now two things happen. You end up with producing another positive charge. And that positive charge, because we have to conserve charge, we only have one charge here, so you can make a positive charge. Now, neutrons are not really protons plus electrons, but they have some properties kind of similar, and so you want to make something like an anti-electron, so a positron. And then the positron doesn't go very far before it bumps into an electron. The two annihilate each other and give off two gamma rays. There's the energy, there's the light being given off by the nuclear fusion. Now, when they worked through all the mathematics, they realized that the equation didn't quite balance properly, that you had two protons, and the proton here basically was like two hydrogen nuclei, okay, and we call this H1, okay, and it became, well, something here that also is still just one proton, so it's heavy hydrogen, we call deuterium, and plus a positron, but the equation didn't balance energetically, so they realized there had to be one other particle here, and this is a neutrino. Now that's not really that's not actually a V right there. That's a lowercase Greek nu, but that became this first step in this chain. And so now we have heavy hydrogen, deuterium. Okay. Turns out there's another element of another isotope of hydrogen called tritium, which fuses even easier. So tritium will fuse much more easier, and that's why one of the first hydrogen bombs actually used tritium and lithium as the main sort of thing that makes it fuse, because that was way easier to make it fuse than just trying to throw just regular hydrogens together. So the first step produces this deuterium, which is 2H, which is considered heavy hydrogen. Inside the sun, there's plenty of regular hydrogen that mixes with it, and what you get is something that has 2 protons and a neutron. So 2 protons makes it a helium. So we call this 3He, or helium-3 is how we say that. And because it's helium, but it's not the normal helium that has 2 protons, 2 neutrons. It just has 2 protons and 1 neutron. It's jiggling with energy, quits jiggling, gives off the energy as a gamma ray. And so that's the second step. Now, while all that's happening, the same thing is happening somewhere else nearby to produce another helium-3 down here. So we have a helium-3 and a helium-3, and when they run into each other, they make a regular helium-4, which is 2 protons, 2 neutrons. And, well, if you count up what's on the left over here, we have 4 protons and 2 neutrons. This is only 2 protons, 2 neutrons. So we have 2 leftover protons. That's 2 more leftover hydrogens that go back into the sun and continue the process. And so this is kind of a diagram of the whole thing put together. We got protons come together, they make a deuterium and spit out a positron and a neutrino. The electron bumps into that, annihilation, gives energy going off here. Same thing happens down here, okay? First sort of thing up here made a helium-3, that come together. So this is the proton-proton chain. And the proton-proton chain is one of these things that is happening inside the sun. It's not the only mechanism of nuclear fusion that can happen. There's all kind of different varieties and variants to the nuclear fusion that can occur. Hydrogen fusion can be considerably more complicated than this, but this is the first step of the process. And again, we call it the proton-proton chain, or just the PP chain, because that's easier to say than proton-proton chain. That gives you what's going on. That's how